Yeah, okay, I'm back. So today I'm going to present some joint effort within the IGS SVOT committee. The topic is GNSS attitude modeling. So you can see many authors from many institutions, including several IGS ACs. And the main goal, of course, is to reduce the inconsistency and to improve the transparency in attitude modeling for GNSS satellites. So I'm going to convey four key messages today in this talk. And the first is precise and consistent GNSS satellite attitude are actually very important. The second is modern GNSS satellite require some different attitude models and are therefore not always implemented consistently. So if you check your own software package and compare to the others, you will find significant difference. And the third case is some special cases in the rate limited modeling require some very careful handling. I will go to details later. And the final point is to address these challenges, we have developed a standardized attitude modeling to GNSS attitude. So Tom, maybe you can use this one in the future for the combination. Oh. Okay, let me start with a very brief explanation why the consistent attitude modeling is important. So we know if the attitude is mismodeled, the errors propagate into the satellite PCO corrections, phase wind-up corrections, and the radiation pressure macro-modeling. And all these errors eventually go to satellite products. And this, of course, can lead to inconsistencies between the products generated by different ACs, right? And especially for the clock and bias combination within the IGS, we always have to find a reference attitude, like Tom said, is from Tailgrass, to align the phase wind-up corrections. And for the PPP users, you have, in any case, to apply the same model consistently. So that's the case. A very brief and short introduction and motivation. So I think everybody here are expert for GNSS, but still I try to introduce a little bit about the fundamental part. And most of the GNSS satellite typically using the nominal yaw steering mode. And you can see from this nice figure, the satellite rotates about the Earth pointing axis, and to remain the solar panel axis always perpendicular to the plane formed by satellite, Earth, and the Sun. Because only in this case, the solar panel can face continuously to the Sun, right? And some other regional navigation satellite system like GEO or EXO satellite, they also employ the orbital normal mode. And in this mode, the satellite body is aligned with the orbital frame. And for the nominal yaw angle, we can compute using this very simple equation as a function of the sun elevation angle beta and the satellite orbit angle mu. However, if beta approaches 0 and meanwhile mu is close to 0 or 180 degrees, this equation becomes somehow singular, right? But satellite, of course, doesn't know what is singular. That means the required yaw rate will exceed the hardware limitation, and the satellite need to switch to a yaw rate limited yaw steering mode. So that's the general description. Let's now take a closer look at all the attitude models that are currently available. So you see many. I'm not going to introduce each of them. It's impossible in 15 minutes. But the key message I want to share is we really have a lot of attitude models for GNSS today, and our software package have to support all of them, which is not the case. In line with the previous slide, we also have this one, try to show how different models are assigned to different satellites. And I just would like to highlight the point that for modern satellites, for example, GPS-3, GLONASS-K, and QZSS, they actually employ dedicated implementations that differ a lot than the previous generations. But if you check your software package at home, I'm pretty sure most of the implementations are still following the one from the oldest generation, or simply even assume the yaw stealing mode all over the time period. Of course, that's not good, and that's one of the motivations why we have initiated this joint effort to develop a standardized attitude modeling for GNSS satellite. Okay, that's one thing, and in addition to the increasing number of the attitude models, we also face some special cases in the rate-limited events. For example, the first one, the beta angle sign changes during an event. What does this mean? I'm not sure how many of you are aware of this very special situation, but let me explain by using an example, the catch-up yaw stealing mode for GPS, mainly for the long-term maneuvers. So let's remind a little bit, if we want to compute the yaw during this event, we always need to know the nominal yaw at the event start point, right? And most software packages following the method from Cuba some years ago. And in this implementation, we always use the instantaneous beta angle values every epoch, means this start point is recomputed every epoch. But think about it, if the beta changes sign during the event, the nominal yaw at the event start point also changes, right? Then this will cause a large discontinuities in the computation of the true yaw angle. So that's a problem. And our implementation just try to propagate the event start point by using the beta dot and the mu dot. We always use mu dot, but beta dot, not everybody are using that. Let me show an example here, the impact of the beta sign changes during an event. So in this green curve, you see the result when the instantaneous beta is used. And a clear disadvantage, discontinuity here, right? If the beta angle changes the sign. Well, for the blue color, it's a result by using our method. Then the discontinuity disappears and the yaw is continuous all through the event. That's one thing is the green color is wrong, but the blue color is correct. And the difference can be several tens of degrees. The second case is if the first processing epoch is already in the event, then that's also problematic for some algorithm. So here I take the Galileo FOC model as an example, and the background is still we need to know the event start point. But if the first epoch already inside, we lose the information of the start point. Then we have to propagate back. Then usually we only consider the mu dot, but not the beta dot. Then in this case, we need to consider both the variation and make a consistent backward substitution or propagation. So this can be solved by doing like this. I'm not going to show an example here because of the time. And the next interesting point is the handling of GPS Block 2A satellite regarding the yaw rate. I know these satellites are no longer providing services nowadays. It's no longer interesting for the PPP users, but it's still super interesting for the reprocessing campaigns and the long-term reference frame products, because we have no choice in the early years. So here you can see we have some reliable results from JPL, but I found they provided two sets of solutions, REPO2 and REPO3. So REPO2, they estimate in a piecewise constant mode every 6 hours. But REPO3, they estimate every epoch. Then if you look at this figure, and both solutions of the same time period actually differ a lot, even significantly. So what is the consequence of this? I think the most important thing is it will change the post-shadow recovery behavior, or even reverse the rotation direction, right? Let's see a very practical example here. So the up figure shows the analytical attitude modeling by using repo 2 and repo 3 yaw rate. And you can find the direction is reversed for one of the post-shadow recovery periods. And the bottom figure shows an independent reverse PPP validation. So from this single example, it's clear that the PPP, the reverse PPP solution, agrees much better with the repo3 result. But be careful, it's only one single example. We have to do more tests. And to be more like a scientist, we should be careful to draw conclusion without doing too many experiments. So that will be the next step. And this kind of special handling is another motivation why we want to do the standardized GNSS attitude modeling framework. And with all these motivations, we have initiated this joint effort within the IGS SVOD committee. And of course, this framework is intended to serve as a transparent and consistent and reducible reference implementation for the attitude modeling. And the goal, of course, is to improve the consistency between IGS analyze centers and also between user and the products. And right now, we already considered all the available models, so it should be able to support all the currently available models. And of course, in the future, the SVOD committee will be responsible to do the maintenance and the updates. So if I'm still the chair, I can only promise in this case. So let's see, the good news is it's already, a draft version is already available. And we have many contributors already did the first round test or validations. And the results show very good, consistent across independent software packages like Bernice or even from Canex or from GFZ, from Wuhan, and so on. So, but it's still not yet the final stage. So we are planning for some more test campaigns, including the special case, more tests for the special case, because it's difficult to find one special case. I only found one so far, maybe, but there should be more. And also for the reverse PPP of GPS block 2A, I would still see this is important for the reprocessing campaigns. And in the near future, we will, of course, plan for a joint publication and put everything in the public HIT repository, because everybody should be able to use it. And as I mentioned, I will try to maintain this within the IGS SVOD committee. Okay, thank you.